In this video, I want to look at calculating the length of a vector as well as the distance between two vectors. Let's suppose we have a vector v. In this case, we refer to the length, also known as the norm or the magnitude, with this symbol here. And we just read this as the length of v, the norm of v, the magnitude of v, depending on which one of these terms you prefer. Let's think of a vector in R2. So we know we like to think of vectors as starting at the origin and then having our terminal point, which I'm going to call v1, v2. Well, from this, we can actually use the Pythagorean theorem to determine the length of this vector. So the length of this side is just the value of x. The length of this side is the value of y. So using the Pythagorean theorem, we have that the hypotenuse squared is equal to the sum of the legs squared, a squared plus b squared equal to c squared. Taking the square root of both sides is v1 squared plus v2 squared. So this is how we would find the length in 2 space. And there are similar extensions in higher dimensions as well. So let's suppose I have a vector given by v1, v2, v3, etc. up to vn. Then the norm of v, the length of v, or the magnitude of v, is given by the square root of v1 squared plus v2 squared plus v3 squared, etc., all the way up to vn squared. So let's look at an example. Let's suppose I have the vector negative 3, 2, 1. To find the norm, I need to do the square root of negative 3 squared plus 2 squared plus 1 squared. Or the square root of 9 plus 4 plus 1. So the length of this vector is the square root of 14. If instead I have the vector 2, negative 1, 3, 5, then we can say the length of v is the square root of 2 squared plus negative 1 squared plus 3 squared plus negative 5 squared. So this would be the square root of 4 plus 1 plus 9 plus 25, which equals the square root of 39. So the norm of this vector, or the length of this vector, would be the square root of 39. First, it's always greater than or equal to 0. I'm taking a bunch of numbers and squaring them, which makes them all positive, adding them up, which makes it positive, and taking a square root, which would be positive. So this thing can never be negative. It's equal to 0 if and only if the original vector v is 0. This comes from the fact that I'm squaring a bunch of things and adding them up. So I'm adding up a bunch of positive things, or 0 things. And so if I want them to add to be 0, they must all be 0 in the first place. Next, the norm of k times v is the absolute value of k times the norm of v. So if I multiply a vector by its scalar and take the length, it's the same thing as taking the length of the original vector and multiplying by the absolute value of the scalar. And I won't directly prove this, but you can try to do it and work it out and see why this is true. The next thing I want to look at is a unit vector. These are vectors of norm 1. These vectors are very useful for specifying a direction when length is not relevant for the problem at hand. And we can actually obtain a unit vector in any desired direction by choosing a non-zero vector in that direction and then multiplying by the reciprocal of its length. In other words, if I wanted to define a unit vector u in the direction of v, I would do 1 over the length of v, 1 over the norm of v, times v. And this would actually be a unit vector. So to show that that's true, I'm going to take the length of u. Well, that's going to be the length of kv, where I'm going to let k be equal to this 1 over the norm of v. My last property told me that this is the absolute value of k times the length of v. Well, k is just 1 over the length of v, which is always positive, so I can ignore the absolute values, times the length of v, which works out to be 1. So this is a unit vector, and this is known as normalizing v. As an example, let's consider the vector -1, 2, 2, and I want to find a unit vector u that has the same direction as v. I'm going to start by finding the length of v. This would be the square root of -1 squared plus 2 squared plus 2 squared. That's the square root of 1 plus 4 plus 4, or the square root of 9, which is 3. So my unit vector would be 1 over 3 times the original vector, -1, 2, 2, or -1/3, 2/3, 2/3. And you can check to confirm that the length of u is in fact 1. I'm not going to here, but you can double check your problem that way. And I want to look at defining the standard unit vectors. So the standard unit vectors correspond to the directions of the coordinate axes. So if I think in 2 dimensions, I want a vector going out in this x direction, a vector going out in the y direction. We refer to these as I and j. I is going to be 1, 0, corresponding to the x-axis. J will be 0, 1, corresponding to the y-axis. And if I want to look in R3, I have my vector I, which is 1, 0, 0. J will correspond to the y-axis, 0, 1, 0. And then we use K to correspond to the z-axis, 0, 0, 1. And we can generalize these into higher dimensions as well, where we just let all of the entries be equal to 0 except for one of them, and we just slowly change which one is equal to 1. And the really nice thing about these is that every vector in our space is a linear combination of our standard unit vectors. As an example, if I want to think of 2, -3, 4, well, this would be 2 times I minus 3 times j plus 4 times k. And you can confirm that if I multiply 2 times this I minus 3 times this j and 4 times this k, it'll get us back here. If I want to do 7, 3, -4, 5, in higher dimensions, instead of using I, j, and k, we use e. So I would use 7e1 to indicate the vector that looks like 1, 0, 0, 0. 3 times e2. So e2 would be 0, 1, 0, 0. Minus 4 times e3. E3 would have a 1 in the third spot, 0, 0, 1, 0. And then finally, plus 5e4. And e4 would have a 0, or I have a 1 in the fourth spot. Next, let's look at the distance between two vectors. Let's let u be u1, u2, etc. through un, and v be v1, v2, etc. through vn. Then the distance between u and v, denoted by d of uv, is the norm of u minus v. Equivalently, the square root of u1 minus v1 squared plus u2 minus v2 squared, etc., all the way up through un minus vn squared. So let's look at an example. Let's let u be equal to 1, 3, minus 2, 7, and v be equal to 0, 7, 2, 2. Then the distance between u and v, this would be the square root of, and we subtract 1 minus 0 squared for the first coordinates, plus the second, 3 minus 7 squared, plus the third, -2 minus 2 squared, plus the fourth, 7 minus 2 squared. So as we work this out, this is 1 squared plus minus 4 squared plus minus 4 squared plus 5 squared. Or 1 plus 16 plus 16 plus 25, which works out to be 58. So the distance between these vectors u and v is the square root of 58.